Okay. Okay, let's start with the lecture talking about prediction methods.
Están grabando.
We introduced some concept yesterday talking about empirical, statistical, and physical deterministic models. Now, when you use one and when you use another one, you usually use the empirical statistical model in the design phase of the network. Because they are very fast. They are reasonably accurate, but they are fast. So you can quickly design your radio network. You can optimize, you can run several simulations to optimize your network without losing too much time. While the physical deterministics can be used in the deployment phase. Once you have designed your network, in the deployment phase, you can optimize, slightly optimize the position and the radiation pattern of your antennas using a physical deterministic model that is more precise, even if it is more heavy from a computational point of view. But you don't have to run it too many times because you already designed the network. So it's just an optimization. What we shall see first. We start looking at models for rural areas. We're talking about empirical statistical models. Built-up areas will follow later on. Now, what is the reference model for this, for rural areas? There are several empirical statistical models that are available, but the reference are those proposed by the ITU, International Telecommunication Union radio section. There are several sections of the International Telecommunication Union. R is for radio communication, then there is T for television, and there are mainly related to standards. But propagation recommendations as far as propagation is concerned, are developed by IT1. Those are very simple algorithms, in particular, reasonably simple algorithms. In particular, for the propagation prediction in rural areas, the recommendation that that is relevant for us is the P, that stands for propagation. You will find a lot of recommendation under this code 1546-4. And the title is Method for Point to Area Predictions for terrestrial services. Now, once up to a few years ago, let's say 3-4 years ago, you had to pay to get those recommendations. Now they are freely available, luckily. But anyway, I have the recommendation at hand, so later on I will send you a copy of this recommendation. And what is the scope of this recommendation? This recommendation is applies in the frequency range 30 megahertz to 3 gigahertz. Distances from the station from 1 to 1,000 kilometers. And TX antenna height above the ground. Up to 3,000 meters. Usually the receiver is lower. How it is structured, how it is built. This model is empirical statistical, so it is based on interpolation and extrapolation of experimentally determined from empirically derived data. They have been measured for several frequencies, distances, and then they have been interpolated to obtain data for different frequencies, distances, etc. Now those graphs, if you look at the recommendation, you will find graphics. I will show you. We will comment. I already sent you the graphics, but we will comment them so you can understand what they are. You will see dependence on distance, antenna height, frequency, obviously, nature of the ground, and percentage of time. This is important because we know that situations, that the atmosphere situation in particular is changing all the time. So in particular, the curves that you will find on this recommendation are for an equivalent isotropic radiating power of 1 kilowatt. You will find actual numbers of field strength, but those field strength are being calculated for an effective isotropically radiating power of 1 kilowatt. So if your power is different, you have to renormalize the curves. And the frequency that been measured are 100, 600, and 2000 megahertz. And length or C. Now, this measurement campaign has been carried out mainly in Europe and North America. So those data refers to temperate climates. In particular, as far you will see, if you look at the recommendation, you will see, as far as C is concerned, a classification in warm sea and cold sea. Warm sea is the Mediterranean, where the measurement has been done. And cold sea is North Sea, towards the Arctic. Now, what was this? Unfortunately, that's where the measurement campaign has been made. So there is now a lot of recommendations. Almost all of them are going to be right. Now we are going to collect data from a tropical and equatorial climates. But the procedure is just starting. So some of the scientific research that is being done now in propagation is to assess those models against measurements carried out in equatorial and tropical climates. So it's just started. We've done some work, in particular in, I've done myself some work with my colleagues in Malaysia, in equatorial climate and for satellite propagation, but there is a lot of groups that are doing measurements in India, Nigeria, this kind of places. It would be interesting to have a setup also here. We're working out, we can see, we are trying to see with Professor Ramos if we can set up an experimental measurements and explore it. But let's go back to our things. Now, in the curves that you find on those, on the graphs that are being produced by RQR, show the field strength exceeded that is the minimum value of field strength. The value of field strength that is exceeded for, you find several curves, 50% of the time, or 10% of the time, or 1% of the time. So 50% is the standard atmosphere. And for curves show the field strength that is exceeded for these percentages of time, and this is important, for 50% of locations, 50% of points within an area of 500 times 500 square meters. So the numbers that you find are representative for the field that is exceeding in alpha points. Let me show you what those curves look like and how we can use them to do our calculations. That's what's shown yesterday. So the model we are talking about RM is RM, heuristic statistical. If you go through the I2R recommendation, you find curves like this. You should have a better copy than I sent you. So maybe you can refer to the figure that I sent. What is shown here? Here you have those kind of graphs where you have frequency, which is, for example, is 100 megahertz, and refers to, I hope you can read it, but you have a copy of this. Length path, 50% of the time. So those diagrams refer to what you can expect at 100 megahertz over length for 50% of the time. Now you have here distance in kilometers. This is a log scale, so you have 1, 10, 100, and 1,000 kilometers. And here you have field strength in dB with respect to 1 microvolt per meter. So it's electrical field strength, dB with respect to 1 microvolt per meter. The reference line, the straight line here, that is indicated as maximum, is free space. So this line, this straight line here, is the electrical field that you would expect in free space. And this is the maximum that you could achieve. Now you have a set of other curves of different colors that refer to the height of the transmitting station. The receiving station is at 10 meters above the ground, fixed. It's kind of average height for TV receiving antennas. So what you can say that what can we see that you can see that if the transmitting antenna is quite low, the field strength that you have for a given distance is much weaker than the one that you would have in free space. And this is always the case if the antenna is low. You tend to the free space situation at short distances if the transmitting antenna is quite high. In this case, it's 1,200 meters. This is because of the effect of the ground. So even if you are very close to the transmitter, we are talking 1 kilometer, if the transmitting antenna is low, you will have an electric field that is much smaller than the one that you would have in free space. Now, when your distance increases, you go down parallel to the free space curve, so you follow the free space curves up to a great point when the electric field starts to decrease much more quickly. This is because here you are below the horizon of, you start to go below the horizon of the antenna. So you have your transmitting antenna. After a certain point, after a certain distance, you start to go below the horizon. But we know that because you have diffraction that we have seen yesterday, the signal does not drop to zero when you are below the ozone. So the diffraction still allows you to receive a significant field, even if you are 100 kilometers, 200, 300, if you are quite below the horizon. This mechanism is diffraction. Obviously, the further you go, the quicker and the weaker the signal becomes with respect to free space. Now, we can comment this other diagram, and then I will tell you how we use it really for our applications. This is the same thing, but for CPAT, 50% of the time, but on C. What you see is that on average, the signals over C tend to be slightly stronger. Take a given distance, those curves are a little bit higher, not too much, but tends to be a little bit higher just because the C is a vector conducting, it's got a higher conductivity with respect to the ground, so you have less losses. I won't enter into the details, but the behavior is very similar, but you get a slightly stronger signal over the C. Now, just to show you what the difference is when you change time percentage. Those are 600 megahertz, a different frequency. CPAT over C, both of them. This is the signal that is exceeded for 50% of the time, and this is signal that is exceeded for 1% of the time. What this diagram is telling us is that for a given distance, obviously, when you go from 50% of the time to 1% of the time, the signal, the level of signal is much higher than 1% of the time. That is, in other words, if you need this value of electric field, for your system to work, it will work only for 1% of the time at this distance. Because here it will be much lower. The exceedance probability, the signal exceeded for 1% of the time is obviously much higher than the one that is exceeded for 50% of the time. And this is due to the variation of the refractive index of the atmosphere. We will learn how to calculate this, but this is rather clear in the graphs. So how do we use them if we have to? In my opinion, the best way to use this diagram, if we will use them in some of our applications, since those diagrams are normalized to 1 kilowatt of equivalent isotropic radiation power, we usually have a different value of effective isotropic radiation power. What we use of these graphics is the distance between free space, distance in dB, between free space and the curve that we need. So we are not really looking at the absolute value of the electric field, but at the distance between those two curves. So we do our calculation in free space, and then we introduce the extra attenuation by evaluating this distance. That's, in my opinion, the best way to use those diagrams. If it is not clear now, I think it will get clearer when we do some applications, some exercises later on. There are questions? Okay, well, if we do not want to have electric feedback, we want to have transmission loss. Okay, as I said, those graphics are available only for those frequencies and those for this power and those frequencies. If you go through the recommendation obviously has a wider scope. So in the recommendation you find an algorithm that you can reasonably easily implement in MATLAB, for example, that allows you to extrapolate the data that have been measured at those frequencies for those percentages of time for different situations, that is, for different geometries, frequencies, paths, percentages of time, antenna heights, etc. Even terrain angle with respect to the horizon. But you have to keep in mind that those things are extrapolation. The actual measurements, the actual measured data have been measured at those frequencies for those situations where the graphs are. So now, if we are interested in transmission loss and not in electrical field level, the conversion of those numbers that we find on the graphics to transmission loss is very easy because you have just to introduce some constants. It's 139 plus 0.3 minus E plus 20 log F. And those are dB. Transmission loss in dB. In this expression, the E is the field strength that you find on the figure, on the graphs, on the table. So it's field strength in dB with respect to 1 microvolt per meter. The same scale that is used, the same unities that are used on the graphics that I've shown you for 1 kilowatt. So this is actually what you find on the graphics. You don't have to make any conversion. And F is the frequency in megahertz. Frequency of interest. Depending on the graph. So this allows you to calculate, to evaluate the transmission loss directly from the numbers that the IPUR model uses. We will briefly discuss other IPUR model when the times come. But really there is not much to say about the IQR models because those are empirical models. So they've been built by making a lot of measurements and interpolating the data. There is not much physics in those models. Just a good interpolation exercise. Now, there are better models. And the one that is quite interesting. On the book that I gave you, there are discussions about several models, several empirical models, including this one, and including the one that I will present now. Those two, in my opinion, are the most useful one. In fact, they are most used. So, but you will find the references to the other ones on the book. The other model that is more complicated, more sophisticated than the IQR is the so-called long linearized model. Again, it predicts median path loss. Now the scope of this model works at frequencies between 20 megahertz and 20 gigahertz. For distances from 1 to 2,000 kilometers. As usual, antenna peaks, antenna heights up to 3,000 feet. This model was developed by Longley and Rice initially for point-to-point links, but then it has been extended to wide area coverage, point-to-area coverage. Now, the algorithm adopts three different strategies when it is depending on the distance from the transmitter. So it's quite clever. So if you are at distances if the distance is less or equal to the smoother horizon, the smoother horizon is below. If you are up to here, so if you are up to here, the model uses the two-ray direct and reflected ray reflection theory that we have seen. Plus, if you have obstacles, diffraction losses. The two-ray electromagnetic theory is the one that we are seeing when you have interference between the direct and reflected paths, so you have all that fluctuation in the signal. If you are at a distance that is just beyond the horizon, it uses a weighted average of night fetch and smoother diffraction. If you are just in this region here, this is going to be B, going to be A. If you are just beyond the horizon, obviously there will be no direct or reflected electromagnetic rays, so the only contribution is diffraction, and uses a combination of diffraction by the smoother and some knife edges. And if you are well above, if you are well beyond the horizon, diffraction and actually, or for something that we have not talked about because it's not really of interest for mobile propagation, it's forward scatter loss. Whichever is smaller, this or this, diffraction losses or forward scatter losses, whichever is smaller, obviously. Being losses, the smaller, the better. Whichever is smaller. It calculates diffraction losses and forward scatter losses. Forward scatter is scatter due to the presence of the atmosphere, of these kind of things. Since the atmosphere is not homogeneous, you also have some energy that is scattered in the forward direction. And we're not going into the details of it because it's really outside the scope of our work. But you just have to know that the Longley-Rice model does this for you. Now, this Longley-Rice model has been implemented into different codes. In particular, can be of interest for you. This model has been implemented in a software package that is called Radio Mobile. And the good news is that it's free. You can download it from the internet. I'll show you some of results that you can obtain with this code. It's very professionally done, and it can be used for professional application as well. I'll tell you what the limitation is. Okay. Radio Mobile will give you results like this. And now I'll show you how it works. Now this has got the Italian interface, but you can download the Spanish or English interface. There is no problem when you download it from the net. So this is a simulation that we have done for these are the Alps. So what we see, let me do a new picture. Okay, you start from the terrain elevation map. This is northern part of Italy, the mountains north of Italy. And as usually, the warmer the colors, the higher the mountain. So we are working on the coverage of an FM transmitter that is obviously located on the mountains. This is the closest village into the... Now, those maps, those models, they need a digital elevation map of the ground. The good news is that they are available for all the planets for free. If you properly configure the software, when you enter the coordinates of the place where you want to do the simulation, it will download automatically for you the digital elevation map of the ground. Different resolution depending on the part of the world. I think that you find high resolution in the United States, obviously, and average resolution for the other part of the planet. Those maps have been built a few years ago during a mission, a space shuttle mission that did that map with a radar all the planets. So I'll call it a space shuttle radar mission map or something like that. But anyway, you find them for all the planets. So what you can do is you design your system by introducing the parameters of the network, the frequency, the units, how many units you have, transmitters, receiver. You can put in all the data of the transmitter. This is transmitted power, receiver sensitivity, losses, kind of antennas, directive, omnidirectional, anything, the gain of the antenna, height of the antenna from the map, etc. You put in all the parameters of the system, and then you can, for example, quickly evaluate. You choose the transmitter, for example, this one, and you can immediately draw, for example, the optical visibility, the geometrical visibility. In this case, we are going to show things from here, hopefully. Let me see if it works. Yeah. So the colored area means there is a direct visibility between the transmitter, that is here, and any point inside this area. When there are no colors, there is no visibility. No direct visibility. But we know from theory that if there is no visibility, it does not mean that you don't have any signal, because you have diffraction. So this first analysis tells you which places are reachable, directly reachable from the transmitter. Then you can calculate the radio coverage. And this, for example, will show you a map on dB microwatt per meter. Let's see if it works. Maybe I should remove the other map. The scale is not brilliant. This is the direct calculation of dB with respect to microwatt per meter on the ground, where the mobile unit is. So this is doing all the calculation by assuming that there is a unit moving around. You can specify the parameters of the unit as well, obviously. And this is a quite large area, so it takes some time. And obviously the warmer the colors, the stronger the signal. Then you can define a threshold where you don't show just anything, so all those areas that are not colored, there is no usable signal over there. Keeps on asking me. So this gives you an idea of the coverage. You have strong signals here, stronger signals here, average here, then you can see the blocking effect. Those are top of mountains, so there is good visibility. In some lateral valleys you cannot enter, but if you have possibility, you can reach quite places that are far away. You can optimize your coverage by moving the transmitter somewhere else. You can make it higher, change antennas, these kind of things. Another thing that the system does, let me see. In this case, you can calculate the Fresnel ellipsoid from a point to point. Now, this is a very short one because I'm considering a very short radio link here. But this is what you would predict for this very short radio link here that you can see, transmitter, receiver, you can hardly see it because they're very close to each other. But what is important is that you have transmitter and receiver. This is the profile of the ground. They are quite close, so you don't see much. And this is the first, second, and third Fresnel ellipsoid. Let me show you a better image. I'll show you the Fresnel ellipsoid. Okay, this is a better link. You have transmitter and receiver. It's here. Beyond this obstacle. So this is a bottom profile. So this line here is the direct path that is obviously obstructed. And the software tells you, look, there is an obstruction at 61 kilometers from the transmitter. So there is no visibility. you can see that also the first Fresnel ellipsoid, that is, we just talked about the first Fresnel. The software draws the first 3 Fresnel ellipsoids, but we are really interested in the first one. The first one is heavily obstructive because this obstacle is completely blocking the first Fresnel ellipsoid. So this is a serious blockage. But nevertheless, you have some diffraction, knife-edge diffraction from this point. So the software does all the calculations for you and tells you that those are the transmitter parameters, receiver parameters. You require a 6 dB microvolt per meter to work, antenna gain, etc. Does all the calculations for you and tells you that the electric field at the receiver is 21.7 dB microvolt per meter. So it's good enough, because it's larger than this, it's good enough for the system to work. And it tells you that the total path loss is 136.7 dB, including the blockage due to the obstruction. So really does everything for you. And this is done by applying the Longley-Rice technique. This is, for example, another coverage map that has been done. The area here